everyone, and thank you for coming to my talk, even though it's the last one. I'm Ashley Bell. I just graduated from Ithaca College, and I'm going to be attending Colorado School of Mines in the fall. And I'm here to talk to you about quality control and automatic outlier detection of atmospheric radiosonde measurements. So first off, what is a radiosonde? Essentially, it's a weather balloon with an instrument attached to it. It goes up into the atmosphere, and it takes readings like temperature at different pressure levels. So this over here is a UT plot. Basically, all I want to show you with this is that over here on the right side, you can see this is wind, and the speed and direction changes as you go up into the atmosphere. And the two white lines are moisture and temperature, and they also change as you go up. These are launched daily all over the world, as shown in this plot here. There are over 1,500 stations globally, and some of the records date back well into the 1940s, so we have over 60 years worth of data, recorded 2 times a day, which gives a total of 50 to 90 million different soundings that my advisor Joey is responsible for archiving. The data is really important because it's used for numerical weather predictions, and everybody likes to get up in the morning and see what the weather's going to be like for the day. The NCEP, who makes the predictions, uses 20 to 30 quality control techniques on these radiosondes today. That doesn't include stuff that's in our past. So like I said, there's more than 60 years worth of data, so some of it is still needs to be quality controlled. So if we can improve the consistency within the data, then we can use it for climate study, which is really important to us here. So my project goals are to develop a robust and flexible quality control technique that correctly identifies problematic points or outliers. By problematic points, I mean extreme weather events like Hurricane Katrina or something like that, or data errors. So data errors can be random errors that are just throughout the data, or systematic errors that can be used from like a system failure or something where you get a string of errors. My project focuses mainly on the random errors. Also, we really want to automate this process because, like I said, there are a ton of the different soundings, and to manually inspect all of these would just be so time-consuming. And a lot of the variables within the soundings can be skewed or normal, so we want to make a technique that is going to handle the different distributions. And finally, we want to improve upon a previously used method by the NCDC, which is the Lanzante. I'll go into that a little bit more. So basically, what is an outlier? It's simply put something that deviates markedly from the rest of a group. So someone that's outside. But it's really hard to decide what an outlier is because, like I said, we have these problematic points. Some of them are caused because of extreme weather, and they're probably going to look like outliers, like Hurricane Katrina could look like an outlier, but you really want to include that into your data. We want to get rid of things that are just completely erroneous. So back to maybe middle school, we all learned what mean and standard deviation is, or we should have. And so mean in stats, we like to call it basically the center, and the standard deviation is a measure of the scale or the spread of the distribution. But these are easily affected by outliers, which is a very big problem. Robust methods, which is what I'm going to use for our quality control technique, they aim to minimize or just completely eliminate the effect that outliers have on the mean and standard deviation. So there are 2 methods in my project. The Lanzante method, which was used by the NCDC, and they only give one estimate of the standard deviation, so it could be a problem for skewed distributions if you want to catch that tail. And then the Huber, which is our potential improvement, which is an iterative method, but it gives a left and right of the mean estimate of the standard deviation, so hopefully capturing skewed distributions a little bit better. So by a rule, we know that 99.93% of data is within 4 standard deviations for normal data. And so this is like equivalent to one in every 43 years we'd expect to see an outlier. So if we simulate like a month's worth of data here, and we say, all right, let's calculate the mean and the standard deviation. We plot the standard deviation, that's 1 standard deviation away from the mean, 2, 3, and 4. We see that all of our data is within 4 standard deviations. So stats works. But if we add an outlier, anyway, if we add an outlier at 6, which we know is going to be about 6 standard deviations away because theoretical mean of this distribution is 0 and the standard deviation is 1. We really want to capture this and be like, that's really far away from our data. So if we use the standard or the normal method of calculating the mean and standard deviation, you can see from the number up here, the standard deviation jumps up. We plot 1 standard deviation away, 2, 3, and 4. You see from the blue line here that our 6th outlier, or little theoretical outlier that we added, is contained within the 4 standard deviations and wouldn't be considered an outlier if we used 4 as our cutoff. But if we use one of our robust techniques, which here in the green I've plotted the Huber standard deviations at 4 standard deviations away from the mean, it is considered an outlier. So just showing that our methods work. So my research question is the Huber method comparable to the Lanzante method? We know the Lanzante method works because there's a paper on it and people use it. So we want to see if we can improve upon their method and use that. So for my research, I used 84 long-term stations here, globally distributed, so they have more than 30 years worth of data, over 8 different pressure levels for just temperature. And from this data, I completed the NCDC protocol where they did a tier 1 test or a full data set test, where basically they took one pressure level, calculated a mean and standard deviation over the entire pressure level. So you don't get any of the seasonal variability, annual, anything like that, just for the whole data set. And then looked at outliers that were beyond 6 standard deviations away from that mean. And then another more stringent test, a tier 2 test, which is a seasonal one where we took a 45-day revolving window centered around 1 day and computed a mean and standard deviation for that for each pressure level. So it gives you a little bit, captures the seasonal variability and the pressure level variability. We did that for both the Lanzante and the Huber. So this looks kind of scary at first, but don't be alarmed. This is all of the temperature readings at the 850 millibar pressure level for one station in Rochambeau, the French Guiana. So these dotted lines that you see here are the seasonal means and standard deviations plotted 4 standard deviations away from the corresponding mean, which you can't see. There's kind of a faint red line here in blue, but you can't see it because all of those crazy little data points. And then also I've plotted these vertical lines where there are 2 really crazy outliers, and then I'm going to zoom in on it. So first off, I'm going to point out the tier 1 test, which is just that overall test for the entire pressure level, where you see that there's only one, there's no like revolving standard deviation here. It's just one solid line. It's not very informative to us. And if we point out the Huber and the Lanzante ones, the blue is the Huber and the red is the Lanzante, and you can see that they pretty much line up with each other. They're almost like dead on, which is pretty good for us because we want to show that the techniques are comparable and that we can use them. And then the most important thing here is the Gaussian, which is this black dotted line where you see all these really crazy boxes, just showing how effective the standard deviation for that method can be. It's not a robust method. And then if you look, these lines are still here from where I plotted those really crazy outliers. These boxes that you see are solely due to those crazy outliers. So you can see that the Huber and the Lanzante kind of eliminate the effect of those outliers. And another test that we did was plot the z-scores that we got. So we calculated z-scores at 4 standard deviations away for the tier 2 test for the Huber and the Lanzante. So this is our 2-sided, this is the 1-sided standard deviation estimate. And if the methods were not agreeing with each other, we wouldn't see them lining up on a 1-to-1 ratio line, which is this line right here. They pretty much all are lining up right on this line, showing that they're pretty much agreeing with each other. And then we also plotted the Huber z-scores versus the standard z-scores using that Gaussian estimator. And they're not agreeing because they're not lining up on that line, showing that we're really improving upon what the Gaussian would estimate. Finally, these are some confusion tables, which are confusing. But don't be alarmed. We're just going to focus on one point. Basically, what they are going to show us where the 2 different methods disagree. So important here is this top right corner. So this is the tier 2, the tier 1 plus tier 2 Lombardi, the tier 1 Lanzante. And there's only one outlier where they're not agreeing, where the tier 1 Lanzante is considering an outlier, but the tier 1 plus 2 isn't. Showing us that we really don't need that tier 1 test to do the whole thing. And again, for the tier 2 Huber and the tier 1 Huber, we look at that top corner again. Only 2 outliers are considered an outlier by the tier 1 and not the tier 2, showing that we really don't need the tier 1 again for this test. So in conclusion, I've shown that the Huber method is very comparable to the Lanzante method. You saw that with the scatter plots where they pretty much lined up with each other. And then also, it may be possible for us to just completely remove the tier 1 test, which would be an improvement upon what the NCDC did. So for future work, I have 2 weeks left here, and I'm also going to be starting my master's at mine, so this is going to be my master's project. We really want to figure out which method works better, because I really haven't answered that question here yet, but it's kind of difficult to do that. Also, we want to figure out which pressure levels are worse. We have evidence that the upper pressure levels have more outliers than the lower ones, and this is just simply a box plot. You can't really see it because the boxes are so freaking small in there. And so you can see that the 100 millibar pressure level has 200 and the 800 only has 41. It's pretty comparable between the methods. And also, we want to look at other variables such as moisture and wind. Moisture tends to be skewed and so does wind. So kind of back to the statistical kind of stuff. If I plot a skewed distribution, this is just a Weibull distribution that's generally used, and we use the Huber estimator and the Lanzante estimator, and this here is what Weibull for this actual distribution says should be the mean and standard deviation. The Huber better captures that tail. The Huber is this blue one here, whereas the Lanzante doesn't really capture the fact that there's a tail over here, which is pretty important. And finally, we want to do some other outlier tests, not just the tier 1 and tier 2. There are a lot of other things that we want to look at. So here's the references to the paper that the NCDC did for the same sort of project. I want to thank Joey Camone, my advisor, also Doug Nietzsche, he's my advisor, Mandy Herring, who is at Mines, who will be helping me with the project too, Sizzle, Cyparks, and Clara.
Okay, questions? Here you go.
So how do you determine whether one of those outliers is truly an outlier or if it is some sort of extreme weather event? Do you just look at documentation of weather that was happening in that time period to determine that, or?
I think for now what we're going to do is try and take like maybe 10% of our stations or even less, a very few percent, and actually try and manually inspect them and try and figure out how, like the false positive rates, the false negative rates and stuff like that, because we haven't really captured that with this yet, but then eventually we try and find out, you know, what cutoff is going to work the best. And it might not be the same for every station or every pressure level, but that's the point of trying to to develop a method that can change for that.
How did you decide that 4 standard deviations was a good cutoff?
So in the paper that they used 6, but our idea was that because we have the 2-sided standard deviation for the Huber estimator, that we could probably shrink that in. So we tried 4, but we might try other ones too, just to see. That was just for now, so.
So it sounds like the Titanic breaking out. Your Z plot that showed that Huber and I'm going to forget the name right now. Lanzante, yes, positive. That it was trailing off towards the upper right.
Yeah.
It wasn't sort of like bang on all the way. It was
there.
yeah. Is that just not significant, or?
We haven't assessed significance or anything, but there are, out of the entire data set, there's less than 1% of the data that those ones weren't, for that particular station where they were not agreeing, or very close to agreeing, so.
Yeah, it's
something
I'm
that
not
needs to be
seeing the
addressed.
slide, but my recollection was it's right on the line and then it kind of trails off.
Yeah. Right up here is
Yeah,
kind
sort
of
of,
this
there's
little
a
bit
kind
right
of
there.
little, yeah, there's
Yeah.
just not enough data up there for that to really,
You can't see, but this is actually like 30,000 data points.
okay.
Because they're all pretty much concentrated around here. If you think about, most of the z-scores are not going to be up in this 50 range where they're 50 away from the mean.
Mhm.
Most of them are going to be closer to, within that 4
Yeah,
region.
no, I'm just looking at the ones that
But,
mine is 50,
yeah.
and they're all like very
They're pretty
conveniently
close.
lined up like beads on a necklace, right?
So this might be those upper pressure levels, like the 100 millibar pressure level has a lot more outliers. So it just requires a lot further analysis. We haven't really gotten there yet.
Okay. Any other questions? Not, then I'd like to thank our speaker and in fact all the speakers for the past few days.